Welcome to Methods in Biostatistics. Today, we are going to explore a fascinating and essential concept called the coefficient of variance. As biologists and zoologists, you will often find yourselves comparing data from vastly different animals, populations, or biological markers. How do you compare the weight variation of an elephant to that of a mouse? Or the variation in a patient's height versus their blood pressure? By the end of this video, you will understand exactly how to solve these problems using a simple but powerful statistical tool. Let us dive in. To begin, let us imagine you are a biologist studying two very different animals in the field: massive adult elephants and tiny field mice. You measure a group of elephants and find their weights vary by about 50 kilograms. Then you measure a group of mice and find their weights vary by just 5 grams. If you only look at the raw numbers, 50 kilograms seems like a massive variation compared to a mere 5 grams. But is it really? An elephant weighs thousands of kilograms, so a 50-kilogram difference is actually a tiny fraction of its total body weight. Building on our animal example, let us look at the mouse. A typical field mouse only weighs about 20 grams, so a 5-gram difference in weight is a huge percentage of its entire body mass. This highlights a major flaw in basic statistics. To fairly compare the spread or variability of these two completely different groups, we cannot just look at the raw, absolute spread. We need a way to measure the variation relative to the typical size of the animals. We need a standardized metric, which leads us directly to the coefficient of variance. Now that we understand why we need a relative measure, let us formally define the coefficient of variance, often abbreviated as CV. The CV is a statistical measure that represents the relative dispersion of data points in a series around their mean. Unlike the standard deviation, which tells us the absolute spread of data in the original units of measurement, the CV is a unitless percentage. By standardizing the variation, it allows statisticians to compare the degree of variation from one data series to another, even if the means are drastically different. This brings us to the mathematical representation of the coefficient of variance. The formula is beautifully simple. We take the sample standard deviation, represented by the letter S, and divide it by the sample mean, represented by x bar. Then we multiply by 100. Conceptually, dividing the standard deviation by the mean tells us what fraction of the average the spread represents. Multiplying by 100 just converts it into a readable percentage. If the standard deviation increases while the mean stays the same, the CV increases, meaning a wider spread. If the mean increases while the standard deviation stays the same, the CV decreases. Before we apply this formula, let us discuss why it is so crucial in biostatistics. In the real world, researchers constantly need to compare apples to oranges. For instance, a doctor might want to know which measurement is more variable: a patient's height, measured in centimeters, or their blood pressure, measured in millimeters of mercury. Because these variables have completely different units and scales, comparing their standard deviations directly is mathematically meaningless and incorrect. The coefficient of variance solves this by stripping away the units, giving us a pure percentage. It is the ultimate equalizer in statistics. Let us see this in action with a concrete example. A pediatrician is studying the weights of newborn babies. We are given that the newborn babies have an average weight of 3 kilograms, with a standard deviation of 0.6 kilograms. We want to find their relative variability. We apply our formula, dividing the standard deviation of 0.6 by the mean of 3. Notice that the kilogram units cancel out completely during this division, leaving us with 0.2. Multiplying by 100 gives us our final answer. The variation in babies' weights is exactly 20% of their average weight. Now that we have the baby's variation, let us look at the adult men in the same study. The adults have an average weight of 80 kilograms, with a standard deviation of 8 kilograms. Again, we divide the standard deviation of 8 by the mean of 80. The units cancel out, giving us 0.1. Multiplying by 100 gives us 10%. Even though the absolute standard deviation for adults is 8 kilograms, which is much higher than the baby's 0.6 kilograms, the relative variation is only half as much. Relative to their overall size, newborn babies are twice as variable as adult men. To truly grasp what we just calculated, let us look at this visual representation. On the horizontal axis, we have weight in kilograms. On the left, you see the tall, narrow bell curve for newborn babies, centered at 3 kilograms. On the right is the much wider curve for adult men, centered at 80 kilograms. Visually, the adult curve looks far more spread out because its absolute standard deviation is larger. However, the calculation box above shows the truth. Because the adult mean is so far to the right, that wide spread is actually a smaller percentage of the total weight. The diagram perfectly illustrates why absolute spread can be deceiving. This visual intuition leads us to an even more complex problem, comparing completely different units. Imagine a biostatistician analyzing a group of adult female patients in a clinical trial. She measures their physical height in centimeters and their blood cholesterol levels in milligrams per deciliter. She needs to know which biological measurement shows greater variability among these patients. We absolutely cannot compare centimeters to milligrams per deciliter directly. The units are fundamentally incompatible. To find out which trait is more variable across the population, we must strip away the units entirely using the coefficient of variance. Let us calculate the relative variability for the patient's heights first. We are given an average height of 165 centimeters with a standard deviation of 10 centimeters. We set up our formula by dividing the standard deviation of 10 by the mean of 165. Notice how the centimeter units mathematically cancel out during this division, leaving us with a pure decimal number. We then multiply this decimal by 100 to convert it into a standard percentage format. This gives us a coefficient of variance of approximately 6.06% for the physical heights. Now, let us perform the exact same process for the cholesterol levels. We divide the standard deviation of 38 milligrams per deciliter by the average cholesterol of 190 milligrams per deciliter. Once again, the complex units cancel out perfectly, leaving us with a clean, unitless fraction. Multiplying the resulting decimal by 100 gives us exactly 20%. Comparing the two, height has a CV of roughly 6%, while cholesterol is at 20%. This tells the biostatistician that cholesterol levels are far more variable and scattered than physical height, which makes perfect biological sense given the impact of diet and lifestyle. We have covered a lot of ground today, so let us summarize the most important ideas. The coefficient of variance is an indispensable tool that measures relative variability by expressing the standard deviation as a percentage of the mean. It elegantly solves the problem of comparing data sets with vastly different averages, like our elephants and mice. Furthermore, by stripping away units of measurement, it allows us to compare completely different biological markers, like height and cholesterol. Whenever you need to compare apples to oranges in your research, the coefficient of variance ensures your conclusions are mathematically sound and free from the bias of scale. Excellent work today.